Correct. You can see okay? Yeah. So last time we were looking at radiation decay. What was the last thing we did now? Decay, wasn't it?
Yes.
Balance in the equations, yeah. You would have done reactions in chemistry. A material, a substance goes in, and then there's a reaction, and then maybe there's a different substance at the end. And you have the same thing happening here with the radiation. Here's an example here. You have hydrogen 1,1 plus lithium 7,3, and there's some reaction or some process that takes place. It's not important right now what it is, but something takes place, and at the end you get helium 4,2 plus another helium 4,2. You get two of these. How many protons do you have before the process takes place?
4.
And after? 4. And how many neutrons? Neutrons. 4. Because in total you have 8 nucleons, and you have 4 of them are protons, so 4 of them must be neutrons. And what about afterwards? 4. So it looks like the mass should be the same, because you have the same before and after. They're just combined differently. Also, H11. Is that an isotope? It's one from... No. It is an isotope.
No, so this one has 1 proton and 1 electron.
Yeah. This one here has 3 protons and 4 neutrons.
Yes.
And this one here has 1 proton and no neutrons. I thought normal hydrogen was 1 proton, 1 neutron, 1 electron. Isn't that an isotope is when the number of neutrons is different to the number of protons?
Yes.
Yeah. So it's an isotope, we think. Right? And then what about the lithium? Is that an isotope?
No.
Yes. It has 1 extra neutron. How many protons does this lithium have?
3.
And how many neutrons?
4.
So it's an isotope.
Why?
Because it has more neutrons than protons.
We didn't know how many neutrons it has.
We do know how many it has. It has 4. You know now. Good. Is that helium isotope?
No.
No. Okay. So we think the mass here, mass 1, should equal mass 2. That's also we think the momentum here, momentum before should equal the momentum afterwards. We also should think that the energy before should equal the energy afterwards. And we also think that the charge before should equal the charge afterwards. So let's start with charge. What's the charge of this one? Or can we know? Well, I suppose we don't know how many electrons it has. It has 1 proton.
1 electron.
No, we don't know it has 1 electron.
We know because there is no sign of the charge.
Oh yeah, so the charge here is 0. And the charge here? 0. So in total 0. So the charge here should be 0, which means these are both 0 as well. Because it wouldn't make sense if this was a +1 and this was a -1, because they're the same thing, you know, you have two of them. Anyway, that charge is not interesting. They're in other words, if they're neutral beforehand, they should be neutral afterwards, unless you introduce an electron into it. So this is fine. It turns out this is true, although really it's not, but you can pretend it is. This is true. But these two, if you look at the mass before and after, you find that they're not equal here. And if you look at the energy before and after, you find that it's not equal as well.
So there is momentum the same as the mass.
Because the velocities will be altered. Now it turns out the reason is not because that they are different. It actually turns out that the energy is different. That the energy is the same. In other words, this is acceptable, this is fine, but this does not need to be true. It's only these three that need to be true. We have conservation of charge, Kirchhoff, conservation of momentum, Newton, and conservation of energy, Newton as well. But I just said the energy is different. The kinetic energy will be different before and after. So, but the total energy will be the same, but the total mass is not. Anyway, to cut a long story short, what has happened here is some of the mass has been lost and turned into energy. So if you have a situation like this, let's say here, let's imagine before you have 1 AMU of mass, and then afterwards you have 0.9 AMU of mass. You might say, oh, I've lost some mass. This is bad. It's not actually. What has happened is some of this mass has turned into extra energy. Maybe heat energy, maybe kinetic energy, whatever. Whenever the mass has appeared to be, whenever the mass looks like it's disappeared, it's not. It's changed into energy. And now if you consider this, the energy will be equal. Okay? So I'll say it again. Mass can change, but energy cannot. If the mass decreases, it just means some of the mass has been transformed into energy. So now we have mass can transform into energy. True, it is. Okay, so this experiment here, let's see, yeah, I'll show you this experiment that gave you the formula. Are you okay? So imagine this. It does seem unacceptable, doesn't it?
If mass can transform into energy,
Yeah.
then the energy input is not the same as the energy output.
No, it is.
So that means energy is destroyed?
No. In other words, mass is a form of energy. So let me put it, look at this. I have my pen here. Right now you say it has no energy. Okay? And imagine for whatever reason, the mass now disappears out of existence. It no longer exists. And what's left is a lot of energy. So it looks like I just it's okay. It looks like I just made energy. Here, is there any energy? No. And then the mass disappears, and there's lots of energy left now. Where did this energy come from? Well, in fact, at the beginning, the mass is a type of energy. That when the mass disappears, it doesn't disappear, it just turns into energy. It's okay. I know it's difficult. I'll show you the experiment, okay? Look at this here. Here is some lithium. And here we have our H11, and we fire the H11 to the lithium. The hydrogen hits the lithium, and what happens is, what flies this way is some helium, and what flies this way is some helium. So what's happening here is what I wrote earlier. Hydrogen plus the lithium goes to make 2 helium.
What does the line represent?
Oh, it's just like a sheet of lithium at 45 degrees.
So,
It's just a sheet of lithium, that's all. Yeah.
can energy change mass to energy?
Yeah, it can go both ways.
No, can energy change the mass to energy?
Yes. So this experiment here, this was done in 1932. And it was discovered that the mass beforehand does not equal the mass afterwards. What's the energy before here? The energy beforehand would just be the kinetic energy of the hydrogen. And what's the energy afterwards? It would be the kinetic energy, twice the kinetic energy of the helium. And it was discovered that the energy afterwards was bigger than the energy before. And this was quite strange. And it was also discovered that you had less mass. So what's happening here is some of the mass got changed into energy. And you can actually work out how much energy you have. The amount of energy that you get when the mass is destroyed is equal to the amount of mass that was destroyed multiplied by c squared. Or as maybe you've seen it more commonly written, this formula. I'm sure you've seen this before. So whose formula is this? Einstein's formula. Yes.
He got the Nobel Prize for this, right?
He did not actually. He got the Nobel Prize for the photoelectric effect, not for this. What is C? C is speed of light. It's the constant speed of light, 3 times 10 to the 8 meters per second.
This is the constant speed of everything.
Special relativity, yeah. Yeah. Yeah?
Energy or radiation travel at the speed of light can change a mass?
No. I'll give you a very simple example to get the idea, okay? So imagine here I put in 1 kilogram of something, and it doesn't matter what it is, it's 1 kilogram of something. You got that? Okay. I close the lid on it, and then later the lid is still closed. Let's say I put some energy inside of this to destroy it. So whatever, a laser, whatever, I put a lot of energy into it and I destroy it. So we'll call this energy here E. So later there is no mass left, there's just lots and lots and lots and lots of heat energy. I measured the mass here. The mass here is 1 kilogram. The mass here is all gone, 0 kilograms. What's the energy here? The energy here is just E. What's the energy here? It's not E. It's going to be E plus some extra energy. Where did this energy come from, this extra energy? When the mass was destroyed. we can work out how much extra energy that is. It is mc squared. What's the m here that was destroyed? 1. So this is 3 times 10 to the 8 squared. That is 9 times 10 to the 16 joules. It's a huge amount.
How does speed come?
It seems odd that the speed of light should be in this formula, and it's beyond this course the reason why. But as Tal was saying, it comes from Einstein's special relativity theory. The proof is not too difficult, but just proof is a complicated integration, but the formula comes out at the end. And you're right, it does seem strange that the c should have anything to do with this, because it's the speed of light. What's that got to do with this? But it is involved in it. That number's huge. What's 10 to the power of 6? That's mega. 10 to the power of 9? Giga. 10 to the power of 12? Tera. So this is 1,000 terajoules. Is it, sorry, tera is 10 to the 12, isn't it? Oh, yeah, 10,000. Yeah, but then there's a 9 in front, so it's 90,000 terajoules. I think that's the biggest number we've seen in the course. 90,000 terajoules. So in other words, every mass has a huge amount of energy stored inside of it. Like every mass, this pen here would have a huge amount of energy stored inside of it. Tremendous amount. So the question is, how can I get at this energy? How can I take a mass and then release all of this energy that's stored inside of it? That's what we're going to have a look at next. So there are 2 ways to do this. There are 2 ways to release it. I didn't say, here I just said you do something and it destroys the mass. Now I'm going to tell you how you can destroy the mass to release all of this energy. So the first method is something called fission. And yes, you know these.
Breaking bonds?
Yeah, it's like this. So what you would have is, let's go back to our good old friend uranium. Let's say this is uranium 235. And then here we have a neutron. What's a neutron? That's N10. And you fire this neutron at the uranium at a really, really high speed, like a huge speed. When this neutron hits the uranium, this uranium is going to break. What's going to happen is this will break into, well, in this example here they have 3 neutrons, and I don't think they say here which atom it is. Yes, 2 other atoms here. One is called barium, and the other one is called krypton. But no, actually, no, it doesn't matter. It splits into 2 smaller atoms. So, in other words, this is not uranium, and this one is not uranium. Yeah.
When the neutron hits
The neutron hits the uranium, and it breaks the uranium. And the uranium splits into, in this example, 5 pieces. 3 neutrons, and 2 other smaller atoms, which are not uranium. You know, what makes an atom different to another atom is how many protons it has. Okay? So for example, if you have an atom with 10 protons, and you split this atom into 2 halves, 5 protons and 5 protons, then the 2 atoms at the end are different to what you had at the start. Okay. In this example here, it splits into 2 and 3 neutrons break off as well. So in fact you get two different atoms, they're not the same, and 3 neutrons.
What's happened to the one which happened to the beginning?
Sometimes the neutron attaches itself to one of the new atoms, and sometimes the neutron becomes one of the free neutrons afterwards. And we'll look at the different cases in a moment.
Is this something we should know?
No, this is just an example. The key here is fission is when you fire a neutron at an atom and force it to break. What you'll discover is the mass after the breakage is less than the mass initially. Yeah. So here, the mass of N10 plus the uranium-235 will be bigger than the new mass of all of this stuff here. So yes, you're right. Fission is the breaking of atoms, the splitting of atoms by firing small neutrons at them. So the definition is here. Oh, of course, they could ask you this definition in the exam. The splitting of the nucleus of a heavy element, and what I mean by heavy element is something big like uranium, into 2 or more smaller nuclei with the emission or release of neutrons and a large amount of energy. And we know what the formula for this large amount of energy is. What is it? Yeah, E equals mc squared. Yeah.
Neutron, like to acquire free neutrons, is it one way for a radioactive material to decay?
That's one way to do it. But that's radioactive decay releases helium-42, which is 2 protons and 2 neutrons, isn't it?
Yeah.
Anyway, this one here they use neutrons, but I suppose it doesn't have to be neutrons, it just usually is.
No.
Well, what you could do, Joshua, is you could have, like, for example, hydrogen, 1 proton and 1 neutron. So all you really want to do is kind of strip the proton off of the neutron to keep neutron one side, proton the other side, you know. I don't know, actually, I think it would be a type of radiation. We'll have to have a look at it later. Yeah. I have a feeling that it's something decaying, the neutron, you break it off this way. Anyways, who was asking me about the neutron, what happens to it? Sometimes it is freed and sometimes it's not. So I want to have a look at those 2 examples. Can I scroll down now? Do you have this?
Yes.
Yep. Okay. So here's our neutron. And it hits into some uranium. And it sticks onto it. And then, I know it looks strange, but it hits the uranium and the uranium kind of wobbles. Its shape changes a bit. And then what happens is, then it splits into 2. and then one piece flies one direction, and then the other piece flies the other direction. In this example here, if you fire a neutron at uranium-238, this element here will be krypton. Yes, just like Superman, and barium. And of course, I didn't draw it in here, but you have your neutrons as well that break off. I think it'd be 3. Now that doesn't always happen. If your neutron here does not have enough energy, this is what will happen. So the neutron will hit the uranium, it will start to wobble, it will start to wobble, it will start to, I know it looks weird, but it will start changing its shape. It's evolving. What's this? Uranium-238 is evolving, and then go like this. And then it'll go back to its original shape, and a neutron will fly out the other side. I know it looks very strange, but what you have is you have your uranium. The neutron comes in, it hits the uranium, and the uranium starts to change its shape. It wobbles, and then after this process, a neutron flies out the other side.
It's like a balloon.
Hmm?
It's like a balloon, or it's just like a balloon filled with water. Or something like this.
Yeah, and then something stuck on the other side falls off.
Oh, so it's not the neutron that attacks.
Not the exact neutron that flies out.
It doesn't have to be the same neutron.
But so it's in the end of the same thing is that it should be.
Yeah, so the end result is you have your uranium-238 and the new neutron, and this neutron will have the same kinetic energy as beforehand.
Why can't the proton fly? Because the neutron is flying.
This neutron does not have... I think, Tanish, it might be the original neutron. I'll have to check. You would need more energy to free a proton. Because that's what's happening, Joshua. In the first example, you're actually freeing protons. You're splitting them into 2 halves. Neutron does not have enough energy here. So it just hits it, it wobbles, and then a neutron comes out. You're asking me if it's the same or if it's different. The answer to both questions is yes. It is the same and it is different. The reason to explain is complicated. But I suppose you could say when it comes to neutrons, you cannot distinguish neutrons. What I mean is one neutron will look the same as the other neutron. So it doesn't actually matter if it's the same or a different neutron. You can't tell, you can't like put a mark on a neutron to keep track of it. So this is something that you'll do if you do atomic physics. I think it's called I can't remember his name, but it has a name in physics. You can't tell the difference between neutrons. So to me, it's not an important question if it's the same one or if it's a different one. Okay? So this is what happens if it does not have enough energy. So nothing changes. The mass stays the same and the energy stays the same.
Don't the electrons get affected by this process?
Yeah, but at the end they all settle back down. Okay. Okay, so now, yes.
For the first one,
Yeah.
when they separate into 2 different
Yes.
atoms, do they have the same number of electrons?
they would have to have the same number of electrons as number of protons, not necessarily the same number as each other.
Proton.
Yeah, because at the beginning there's no charge. The neutron, does it have any charge? No. And the uranium is neutral. And the neutrons at the end, do they have any charge? No. So both barium and krypton must be neutral as well. So yes, they'll have the same number of electrons as protons. Okay, how can we use this process to make energy, lots of energy? Well, consider this setup. Here you have uranium. I'll just write U for uranium. Uranium 2, well, it doesn't matter right now. And here we have our neutron. If I fire this neutron at this uranium with enough energy, this will split into 2. Will the mass be the same? No. What has happened to the mass? It's turned into energy. So it splits into 2 and we get lots of energy. Q. I'll just write. If I put some uranium here and here, what happens when these hit the uranium? This will also split into 2.
Chain reaction.
That's it, chain reaction.
What's each step?
The pieces that break off from the first collision.
This is how
Other neutrons, yeah.
So they're no atoms. Don't the
No.
atoms hit them too?
They could, but I think it would be the neutron that hits them because the neutron is moving so fast it will get there first.
What if they hit each other? What if they hit each other?
If which two hit each other?
Those U and U.
These two? Oh no, these are all stationary. This is like uranium, a lump of uranium. If these two hit, if these two hit each other, nothing would happen. They'll just bounce off each other because they wouldn't be going fast enough.
What if you would make them go faster?
Well, the same thing would happen, that they would both break into smaller pieces.
No explosion.
I don't think you can make this process more efficient if that's what you're looking for. One sec, I'll just do one more layer. So you have uranium here, 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 and here. So this one will split into 2, then this one will split into 2, this one will split, this one will split. You get energy, 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 and energy here. Right, Tanish, yes.
Is that how atomic bomb works?
It is. This is called a chain reaction. So at each level, you get more and more energy. So here you have Q, here you have 2Q, here you have 4Q. So in total here I would have 7Q of energy. And Q will already be a big number. This is also nuclear fission. Uranium is one material that works well for this, but the other material is plutonium. Also works well for this. Well, here it says uranium-235 or plutonium-239 is best for this process. It works best for this.
This is more expensive. Plutonium, I think.
I think so. Or could this have... Huh?
Uranium is $30.
Yeah, uranium, you see, you can, I think you can get hold of uranium easier than plutonium. So I think uranium is cheaper. Yeah, I still have to look into that. I have trouble believing that it could only be $30. Uranium-235 or plutonium-239 works well for this. I think the uranium is the cheaper option. Yes.
Excuse me.
Yes.
I thought you said uranium was 238.
No, there's different isotopes of uranium. So, yes, it will work for uranium. Uranium, there's 235 and 238, which are both unstable. I'm just saying 235 works well for this particular setup, and plutonium-239 works well for this. Okay, This process, you notice that once it gets started, it just continues. You know, there's nothing to stop it. It just goes on and on and on.
The energy that it releases, does it interfere with the uranium?
Well, it interferes insofar as it collides with other uranium. Oh, you mean the energy? No, the energy will just be heat. So this uranium, if you had it, would be getting hotter and hotter in your hand. Well, maybe not in your hand. Huh?
What about the particles? The atoms are formed, like barium and krypton.
Yeah, what about them?
Does the energy destroy?
No. All that happens is the energy comes out in the form of heat.
Okay.
Yes. Oh yeah, well I'm not saying to stand beside this, you know. But I don't think the barium or the krypton will care if it's in a hot environment. You might, it won't. Yeah. Okay, so we can use this in something called a fuel rod. Fuel rods are made from natural uranium enriched in uranium-235. About 3% of it. So you get some natural uranium, which you can find in, I think Australia has lots of uranium mines. So you get some uranium, and you add 3% uranium-235. So you get natural uranium. Your periodic table will tell you the numbers. Uranium-235 is an isotope. So what I'm saying is you take your uranium-235 isotope and mix it in with your natural uranium.
3% of uranium.
What's uranium?
235. I mean 3% of uranium-235.
No. I don't know what the mass number is for uranium naturally. It's 234, is it? Do you have a periodic table? We can look it up. Anybody? Periodic table? Huh? Great. So, have a look at uranium. Where is it? 238. So uranium naturally will be 238 protons and neutrons. So what I'm saying is, if you had 100 kilograms of natural uranium, you would mix in about 3 kilograms of uranium-235. So the uranium-235 is the one that is responsible for the chain reaction. The uranium-235 is the one that can make the chain reaction.
Okay, what is the fuel rod?
Well, that's what we're to know. Okay. So firstly, what's in a fuel rod is uranium mixed with some uranium-235. The uranium-235 gives it the kick.
Do we need to...
Well, there is a question on nuclear energy in the exam. Now, they won't expect you to remember the percentage, but the part of the question might say, a uranium fuel rod is made of natural uranium and uranium-235, and the question will go on. I'm just putting ideas in your head. Yes.
Why is uranium naturally an isotope?
No, well, not. Uranium-235 is an isotope, and this isotope will, if you had it in your hand, it would feel like it's getting warmer and warmer and warmer. This is because of the chain reaction I was talking about earlier. Now this is a bad thing, because if you just had uranium-235, it will get really, really warm, and then it will very quickly just disappear. So what you do is you mix it in with the natural uranium. It's a bit like you have some really powerful fuel that burns really quickly, and you have some fuel that, doesn't really burn that fast. And you take a little bit of the strong stuff and put it into the weak stuff, so you can create a nice balance. You get the uranium rod will slowly get warmer, but not too fast, so it will gently give off heat. That's what they're trying to do here. So a fuel rod is literally a rod that just seems like by itself it's giving off heat, and you're thinking, where is this heat coming from? Because there's no supply of energy.
So 238, not 235.
No, 235 is the isotope you mix in with the natural uranium. Natural uranium is 238.
How much do we mix the natural uranium?
So go to your local nuclear power plant and get 3 kilograms of uranium-235 and 97 kilograms of uranium-238. Go back to your kitchen and mix them together in a big pot, and you have your fuel rod. Okay? Yes. So these fuel rods is what is used in nuclear power plants. Instead of gas, oil, coal, etc. So one way you can make electricity is you can burn gas, oil or coal, make heat water, turn a turbine and so on and so on. But another way of making energy is by getting the heat from the fuel rod. What do you think an advantage of using a fuel rod instead of burning gas, oil or coal might be? You'll need less material. Not quite. Yeah, well, exactly. Gas, oil, coal will release CO2 when you burn it. Making a fire, it's going to release CO2. Whereas the fuel rod just gives off heat. There's no flame. It just is warm. Like radiation, yeah. So it doesn't release any CO2. But of course, there are problems with this type of fuel as well. Okay. Can I go down? Yeah. Right. So you have 3 different situations here. So if you have the right amount, the process will just go on and on and on and release an energy, and this is called critical. We have a self-sustaining release of energy. To put it in simpler English, we have a steady output of heat energy. If you do not put in enough uranium-235 into your fuel rod, then not enough chain reaction will take place. So instead of getting slowly warmer, it will just cool down. Nothing will really happen. So if you don't put enough in, we call this subcritical. The output of heat decreases due to a lack of chain reaction. If you don't have enough uranium, then when the uranium splits, then it's less likely to hit more uranium if there's not enough of it around. So the output of heat decreases due to a lack of a chain reaction taking place.
How long does this reaction go for?
And you can keep this, if you have everything balanced correctly, you can keep this going for years.
Just one word.
I don't know how long yeah, no, I think fuel rods can last a long time, if they're big enough, yeah.
In which condition do lack of chain reaction occurs?
That's, you know, if you don't have enough uranium-235 in the fuel rod. In other words, if there's not enough neutrons flying around to break uranium. A lack of active neutrons is what I mean here.
Is nuclear energy is renewable or is...
It depends. I suppose technically it's non-renewable, but you might call it green energy. Some people might, because it doesn't release CO2. Some people would say it's not green energy. Not actually clear. It depends on who you ask. And then the last one is the bad one. Too much. Supercritical. Too many neutrons emitted too fast, too quickly, will cause too much energy to be released in too short of a time. In other words, an explosion. i.e., explosion time. Now the next thing I'm going to give you is something that they have asked on the exam for a definition. So they haven't asked for a definition of a fuel rod, but they have asked for a definition of something called a moderator. So that's what we'll have a look at next. Okay. There will be a little bit, but this question, they'll ask you for a definition of fission, fusion, which we'll do in a minute. Fuel rod, I don't think they'll ask you the definition of a fuel rod, but they have asked you for the definition of a moderator, which I'm doing next. A moderator will slow down the neutrons. In other words, it will take energy from the neutrons. And the material which is often used is something like graphite. Graphite is a really good material at absorbing neutrons, that's all. Well, what I mean by that is, if the neutron hits the graphite, well, not necessarily absorb, sorry, if the neutron hits the graphite and it bounces off of it, or if it goes through the graphite, the neutron will have a lot less energy. By absorb, I mean absorb its energy, not so much the neutron itself. It will absorb the neutron's energy. What's that, Joshua? Well, these materials will do fine, it's just, I'm saying the graphite will work the best. What's that? This is normally graphite.
Why do you need so much?
Well, we don't want a supercritical situation. So if too much neutron activity is taking place, you want to kind of stop that from happening. So you need to put into it some graphite to start taking energy from the neutrons.
So did they just throw a bench on
Well, no, I'm going to draw the diagram now for how the power plant works. If it's in a supercritical state, you want to release more graphite to try and absorb the neutron's energy and slow the process down back to critical. Okay. So, DIY, this is how you make your nuclear power plant, alright? First, you go to IKEA and pick up your nuclear power plant pack. And inside of it you'll have, number one, you're going to need a shield. So something like lead or concrete. So you need a little gap here, and then a little gap here. And this is the shield, the shielding.
How thick should it be?
I'd say you'd want to make it at least 1 meter of concrete.
Thick or long?
Oh, you want a 1 meter concrete wall around all of this building. 1 meter thick.
Oh, okay.
Yeah, so like these walls here are probably only this thick. You know, you'd want at least 1 meter of concrete. At least. I'd feel better if it was 2. Okay. Alright, so you have inside here, I'll draw them in green. These are in green the uranium fuel rods. Let me just move this word to the left. I need to make a bit of space. And this one here, that's the fuel rod. Okay, now this is inside of the container inside of it as well. Here in black, around the uranium, these are the graphite moderators. I'll just draw that a bit better. Graphite, 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 and graphite. Okay, and then I'll do it in red here. You have something called the control rods. And these control rods, you can change the height of them. So my first control rod, for example, this control rod is not over the uranium. Maybe my second example, I'll draw most of the uranium is covered by the control rod. We'll get to all this in a moment. And then in the last example, we'll say the uranium is not covered by the control rod. And the control rod is also made of a material that can absorb the neutrons, that can handle the neutrons. So control rod is a lot like a moderator as well, except I think it's a much more stronger material. The material usually used for the control rod is something like cadmium or boron steel, which sounds expensive. Okay, now I have 2 holes here on purpose. So this here this is a pump, and in here is a cool material, like a coolant. It could be an oil or water or whatever, but it's some cold liquid. Oh, sorry, and this whole structure here is surrounded by a box, a conductor. No, but you could have the diagram and ask to identify where the control rod or the moderator is.
Why is that code?
Well, what's going to happen here? Well, we'll go through the process in a moment, okay?
Cool it down.
Because it doesn't like being hot. Alright. So let's have a look at what happens here. So in this diagram here, one of the fuel rods is covered by the control rod. So the one in the middle, all the energy that's coming out of it just hits into the control rod and the neutrons are then captured, and that's really the end of the story. Whereas the other two, the control rods are removed. So the neutrons start to be released and they hit into other uranium and it starts getting hotter and hotter. The reason we put the graphite, the moderators, in between the fuel rods is because you don't want the two fuel rods to be working together. You know, you want each one just releasing energy. You don't want the two rods putting energy into each other, making them even hotter. So in other words, the moderator there just tries to balance the release of energy. If you put all the control rods down, there's no energy, because what happens? All the fuel rods are covered up by the control rod, so none of the energy comes out. Okay. In this example here, two of the fuel rods are releasing energy, and one of them is not. What happens is cold oil or water or whatever comes in here, is pumped in. Oh, come on, what's going on here? Oops. Cold water comes in, and this fills up all with water. Of course, this case will get warm from the uranium, so the water heats up. So the water gets warm. And then the hot water comes out here. Now when I say hot, I mean like... No, I mean really hot. Okay? Well, it's not going to be water. It's going to be something that has a high boiling point. So, like an oil or something, it'll be over 100 degrees. Then what they do is they cool it down with water. So what happens later is, if this is something like a hot oil at, let's say, 150 Celsius, this is called the heat exchange. So what they do is they put cold water onto this. What happens when the water reaches 100 degrees? It'll turn into steam, and then the steam will spin a big turbine to make kinetic energy. And this is the process. So you need to be near a water supply here. Okay, so usually these things are near rivers or ocean or something. This is a nuclear power plant. You have a cold water that you turn into steam, and you have some oil that gets pumped all the way around, because then what will happen is this will connect back up here. No, you're not, well, whatever it is, it has a really high boiling point. I guess it's not really a big deal if it turns into gas in the pipe. But you would prefer it not to do this. So after the water cools the oil down and turns into steam, it's pumped back in. So it just goes around and around like this. So actually, what energy does this need? It doesn't need much energy. It just needs the energy for the pump. But you get a lot of energy out of it. What's wrong with this process? So what could go wrong? Yes, but what part of this system can break that would cause it to go supercritical? The control rods would be the weakest point, yeah. What could happen? Yeah, well what would happen is, imagine you have all the control rods open, so they're all full. Okay? And the nuclear, it's getting hotter and hotter, and you're like, okay, now it's hot enough, I need to put the control rods back down, so to stop the energy increasing. But of course, what in the last nuclear disaster and the previous one as well, the problem is always because the control rod jams. So you try to push the control rod back down and it's stuck. It won't go back down. This is what happens. But then if you leave it closed, it's not releasing any energy. You see, this is the thing. You remove the control rod and you let it warm up, and then when it starts getting too hot, you don't want it to go supercritical, so you put it back down. And you might say, why don't you just leave it at a safe level? Because the reason is, the amount of energy it needs to produce will change during the day. So during the day you need more energy than during the night. So maybe during the day the control rod is up all the way, and during night it's down. So then what would happen is, maybe in the evening when the control rod is to go down, it gets jammed. It doesn't go down. So what do you do then? So what do you think you can do here? If the control rod jams, what is the safety mechanism to try and stop it going supercritical? Ron? You're not too far away.
Let the water from your supply going.
Yeah, this is what you do. If the control rods jam, it will continue to heat up. What you immediately do is your water supply, you redirect it to the reactor core. So you literally dump all of your water into the reactor core and you just let it run through. You know, so just flood that with water. And the water will get really hot, so you just let it flow through. So as a safety mechanism, what you would have here is the option of taking the water supply here and dumping it inside of it and letting it come out at the bottom. So there is a valve here. In emergencies, you fully open the valve and let the reactor core, this is called the reactor core, fill up with cold ocean water, river water, whatever. This is the same thing that happened in Japan and happened in Chernobyl as well. This is what they have to do. You have to dump it with water. Now this isn't a solution because it will continue to heat up. All that you've really done is slow it down until you can find out a way to get the control rods back over the fuel rods. So although this makes a lot of energy and it's simple enough process, it does have its dangers as well. Okay. I think some countries like France have a lot of nuclear power plants. Some places like Ireland do not have any. I don't think nuclear power plants are, I mean, I know you've seen in the news disasters in Japan. It's dangerous, but I think the big reason why this is not a good idea is because it's very expensive to do. Because there's a cost here which you can't see. When the fuel rods are used up, you have to then dispose of them. So what do you do with the uranium at the end? Because that's dangerous to people. So what do you do with the fuel rods at the end? Put them out Thursday morning for the garbage collection? No. Yeah, and wake up with Hulk superpowers, you know. One thing that's done, what they do in France is they cover the uranium in concrete and then bury it at the bottom of the ocean.
What's happened next? What's happened?
Well, what they discovered is the concrete has cracked and the uranium is being released. So now you have to go back down and cover it up. In other words, although you get a lot of cheap energy at the start, you pay a lot for cleanup. But then the worst thing is, the energy company which ran the nuclear power plant wouldn't exist anymore, so then it ends up that the government has to pay to clean it up.
And they just finish it.
No, what will happen is the company will go bankrupt or something.
Finish in the area going to it. They should finish the road.
No, what happened is the uranium-235 will disappear. So you're still left with natural uranium, which is radioactive.
And you take those data.
Yeah, and put it back in the earth, yeah. What's that?
Can't need it.
Yeah, well, this is the other thing. You can reuse it, but of course, then this means you have to put uranium in. Like there are places in the UK. There's a place in Sellafield that takes old uranium and recycles it. I'm not sure the process, but they take the uranium and they do something with it so they can use it again some way. So you're right, but of course this also needs money to do it. And again, it's usually government money. So this is not the way forward for energy for planet Earth.
Can't they store it into space?
Yeah, but you have to build a rocket, which also is quite expensive, you know?
Fire something else.
Or store it into the Earth as well?
Or cross over.
Many radioactive isotopes remain radioactive for a long time. They have half-lives of thousands of years. They will have to be stored in a secure place away from people for thousands of years. So at the bottom of the ocean, outer space, wherever you can put it. And of course there is another thing to this as well. You have nuclear weapons, of course, because you think, oh well, this is bad if it explodes, unless it explodes on people you don't like, and then it's a nuclear weapon. So how do nuclear weapons work? Part 2.
Give us a break. We're taking you for the fourth hour.
No, you can manage, you can handle it. We'll just finish early.
Well, what happens if they actually store it into like lava?
I don't know if this has ever been done, so I cannot say for certain what would happen if you throw them into lava.
You go to Iceland.
Yes, you tell me how that works for you. If I don't hear from you, I assume it went well. Yeah. Okay, so for nuclear weapons, you have your uranium-238, and it is shaped as a sphere, so you have it as a sphere shape. And then what you have packed around the uranium is an explosive, a plastic explosive usually, something like C4 plastic explosive. Now this isn't carbon 4. I'm sure they use it in a lot of first-person shooters, right? Call of Duty, yeah. So C4 plastic explosive. And this is really all a nuclear weapon is. What happens is the C4 explodes at the same time all around the uranium. And this will cause some of the neutrons to be put into motion. They'll start to move. These neutrons hit the uranium and then you have your chain reaction process. So in other words, the C4 is the energy that gets the process started.
What's C4 mean?
I'm not sure, it's a plastic explosive. Not too tough. The C4 will start the chain reaction.
So they explode.
Yeah, so the C4 explodes, come on, focus now please. The C4 explodes around the uranium. This will cause some of the neutrons to move. These neutrons will then hit the uranium atom and then the chain reaction starts. And just like with the nuclear power plant, you want the right amount of uranium. If your uranium amount is too small, then the process is subcritical. So you want the minimum amount, the critical amount.
What if you put too much and it's still the same result?
If you put too much, I don't think it's as efficient as if you had the critical amount.
Okay, so what would happen?
No, it would still explode. But I mean, if you the thing is, if you have more uranium, then you need more C4 explosive. And you would need more C4 explosive, but it would need to be a bigger explosion for the uranium. So the price you pay then is you'd have to have more layers of C4. And maybe then it becomes too difficult to have it all explode at the same time. In other words, the most efficient amount would be the critical. Just enough uranium to go critical. To use the minimum amount of C4.
How big is it?
It's really not that big. You would only need about 500 grams of uranium.
And how much of C4?
Not that much. Kind of maybe a couple of kilograms.
That big?
You would have your uranium maybe about that big, and then packed around that would be the C4. So the basketball size would do it, yeah. It's really not that big. I mean, it will be about this big, and then it will be loaded into like some kind of torpedo.
Why did it load?
Well, it's going to be put onto a plane and dropped over a sea. So you can't just drop the bomb. You need to put in something so it doesn't break up as it's falling through the sky. So you put inside a torpedo shell maybe this big. So the uranium's this big, then the C4 is this big, and then it's inside the torpedo.
Walking around the city, can you just put it very high and just leave it?
Yes, well, this is one of the concerns that they have for terrorist attacks, is that, you know, somebody would just have this in a sports bag, actually was the example that they gave, and just leave it on a train or something somewhere. You're right. The good thing is it's very difficult to get hold of uranium-238. And, yeah, the guy with the sports bag should not be telling me this. No, but you're right, Carl. It is something portable that could be carried around by a person, and this is a terrorist concern as well. Yeah.
How does the neutron fire the uranium?
Now what happens is the C4 explodes. It gives the neutrons kinetic energy. You remember, uranium is very unstable. So if you put some energy onto it, you could knock off some of the neutrons.
So basically that's what a neutron does, it adds energy to uranium.
The neutron is usually what hits into the uranium. So the explosion will shake some of the neutrons off and start firing it into the other uranium. Okay? Let's work out how much energy is in your nuclear explosion. So, Daniel, can you tell me on your periodic table what is the atomic mass of uranium? Well, you have it as uranium-235. Yeah, what's it in the periodic table? Is it uranium-238?
238.0.
Okay. So let's say you have 500 grams of your uranium. What did you say the number was? 238?
Yeah.
Okay. But anyway,
That's the one we need.
that's actually just all we need, isn't it? Oh yeah, we don't need to know anything in the periodic table. But just out of curiosity, this is about 2 moles of uranium. So the amount of energy would equal m a half a kilogram 3 times 10 to the 8 squared. So that would,
4.5.
yeah, 4,500 terajoules. Yeah, 4,500.
45.
Was it 90,000? Oh, gee. 45,000 terajoules. Not bad. It will take out. It will take, not bad for basketball. It will take out a city.
Slam dunk.
What?
Slam dunk.
That's terrible. Yes. Yes. Okay. Remember earlier we said a neutron is roughly 1 AMU and a proton is roughly 1 AMU. I'm going to give you the exact numbers now, which you'll need for this question. They'll give you the numbers in the question, but so you've seen it. A neutron is actually 1.008665 AMU, and a proton is 1.007825 AMU, and then an electron, what's that, minus 10, isn't it, is 5486 AMU, and just to remind you, 1 AMU is 1.66 times 10 to the minus 27 kilograms.
What's the AMU?
It's just roughly the mass of a nucleon. It's just a constant there.
Atomic mass unit.
Yeah. Do you use it in chemistry? No, okay. Now, I'm going to give you a small question to try. So what we have here, calculate the energy when 2 protons, 1 neutron and 2 electrons combine to form helium-3. Yeah. Oh, no, actually, I'll do something else with you first, before doing that one. Helium has how many protons? 2. Now, what I want you to do for me now is calculate the mass of helium. So it has 2 protons and 1 neutron. So tell me how many AMUs it is. Yes, Tash.
No, I'm wondering why is that 3 something?
As an isotope. Are you sure you have it on the neutron as well? It should be about a 3. 2 protons and a neutron.
3.024 AMU.
This is 3.024 AMU. 315 at the end? It does. We need to be precise for these in the exam. No, this in fact is not the mass of helium-3. If you now measure the mass, it's actually this. No. The mass of helium is actually this number here. This might seem strange. You're looking at this going, it has less mass than I expected it to. After all, what is helium-3? It's 1 proton and 2 neutrons. So if I stick a proton and 2 neutrons together, why is it less mass? Well, this is what's happening. You have a proton and a neutron. You've worked out the mass as this. Agreed? That's what you did. When you stick them together to form helium, you need some energy to stick them together. They don't just stick together. There's an energy holding them together. This energy which holds them together, you know this from chemistry, it's the bond, so to speak. This is called the binding energy. Yes. So it's not that it's lost any mass. It's not lost any mass. By sticking them together, some of the mass was changed into energy to hold it together now. And you can probably get the formula to work out the energy. It's the mass which appeared to have been lost multiplied c squared. So if you just minus these two, you get 0.0, well that's a 2, that's a 1, that's an 8, that's a 1, that's a 0. Is that it? I have too many zeros, don't I? Should be just like this. 0.01812 AMU. Alright, well what is it please? 0.0, look, people with calculators type.
0.008285.
Okay, what I'd like you to do is calculate the binding energy here. How much energy is used to keep the atom together?
1.238 times 10 power minus 12.
You converted this into kilograms and you multiplied it by c squared. Oh great, what did you get?
1.238 times 10 power
minus 12 joules.
How is it minus? If you times by 10 6.
No, but remember an AMU is 10 to the minus 27. That's going to be a lot bigger than your 10 to the 8 squared.
And
Change it to kilograms first, yeah.
So this is nuclear fusion.
No. This is just a chemistry thing. This is working out the energy that's keeping the atom together. So there is 1.238 times 10 to the minus 12 joules of energy being used to keep the bonds there. You know, it's a type of potential energy. Look, you did with me and with Lorraine ionization. The amount of energy you need to give an electron so that you can free it from its orbit. Yes? This is a type of ionization, so to speak. That number you got there is how much energy you would have to give this helium to separate protons and neutrons. Okay? So, how could you deliver the energy to this helium? Well, no. You could fire a neutron at it.
Wouldn't it be too much?
So what I want you to work out now is how fast the neutron needs to go so that when it hits the helium and the kinetic energy is slammed into the helium, I want to know how fast it's going so that I can break it. So what kinetic energy does the neutron need to have? The kinetic energy the neutron would need to have would be this much.
Yeah.
So I want you to get me the velocity of the neutron so that it can destroy this helium atom.
The energy is so small.
Yeah, the mass of the neutron is so small, so I think the velocity will be quite large.
7.393
Yeah.
times 10 to the 14.
Faster than the speed of light?
Yeah.
Oh.
3.33 times 10 to the power of minus 9.
Minus, how 10 to the minus what? So a neutron going at this tremendous speed will destroy this helium, yeah? Just think about it before you give me the answer. So anyway, what's the formula for kinetic energy? A half mv squared would need to equal 1.238 times 10 to the minus 12. So V would equal 2 times 1.238 times 10 to the minus 12 all over, what's the mass of neutron? It is 1.008665 times 1.66 10 to the minus 27 square root. Is there something you forgot to do, Joshua? 2 times 1.238 times 10 to the power of minus 12 all over
4.24 times 10 to the power of 8 squared.
That's faster, like.
That's a good nice finish.
377,398,75.
And it's just proof that you need to find an example of that.
It would be 0.377 times 10 to the 8 meters per second, which is roughly 12.6% the speed of light. So quite fast, but not faster than the speed of light. No, impossible. Sorry, Hamish. So there's one last thing to look at. There are two ways to make nuclear energy. Fission, which we did first, and now fusion. Fusion is the safe form, where there's zero risk of explosion. And we do say, yeah. What?
5 minutes. Look at the time.
Yeah, 5 minutes. So let me do it in 5 minutes.
It's fuck around. Look at your work.
Please.
4 hours.
Please. I know it's cruel, but please.
When do you finish your work?
Well, I'll have 3 hours of physics from 2 to 5. Then I'll go home and do another class back home for 90 minutes. Yeah. So my day will go on much longer than this, okay? Right, it'll only take a couple of minutes. The last process is called fusion.
What's this going from?
Fusion is a different way to make nuclear energy. So what material do we use? Yeah. What? It is so much safer. It's actually completely safe.
What's the definition?
Yeah, so that's what we're going into this here. So this is when two light nuclei come together to form a heavier. Two light nuclei unite to form a heavier nucleus with the release of a large amount of energy.
So it's like, works backwards.
Kind of like that. Usually what happens is you have helium 2-1. So this helium here, you fire it at another helium 2-1. So can I scroll down a little bit? So it really is, you have some helium and you fire it at some other helium. How many protons here?
1.
1. And how many neutrons? 1. And here, one proton, one neutron. So how many protons will you have at the end? 2 protons. So what atom is that? Helium. How many neutrons will you have?
2.
You have 2 neutrons. What happens when you do this is this only gets one of the neutrons, and then the other neutron ends up being free. But the mass of helium plus a neutron is less than the mass of 2 helium. Sorry, the mass of this helium and this neutron is less than the... Oh, sorry, I wrote helium here. This should have been... I'm very sorry. This should have been hydrogen. Sorry about that. The mass of helium and a neutron is less than the mass of 2 hydrogen. So what happened to this last mass? It's changing the energy. It creates helium and energy.
Which energy is
The previous one, the fission. But there's a big problem with why this method is not used, even though it's safe. Because if you look at this diagram, there's no chain reaction here. You're just taking hydrogen and you're firing it together. And when you want to turn the power plant off, all you have to do is just turn the power off the hydrogen being fired at each other. So you can turn it off instantly. Just hit the button and the process stops. There's no chain reaction, so it cannot self-sustain. It needs your energy input. This must have a large kinetic energy. So in fact, what's not clear here is that you use a lot of energy to go into it, but the energy that comes out is bigger.
Much bigger?
10 times bigger. So what happens here is Q2 is roughly equal to 10Q1. So if you put a lot of energy in, you get 10 times the energy that comes out. What's that? No, it is conservation of energy. The lost mass is converted into energy. So if this is so great, why is it not used? Why is there no power plant in the world that uses this method? Loss of energy, what do you mean? Well, yes. Problem number 1 is, in my last diagram, what energy did I need? I just needed the energy for the pump to pump the water around. Whereas in this process here, I need a lot of energy to go into it. That's the first problem. The second problem is, this process is not stable. The machine, the nuclear power reactor will run for only a few seconds. It's very difficult to get hydrogen to collide. This one here, when the hydrogen atoms get very close together, what's the charge on the nucleus in the hydrogen? +1. And on the other one? +1. So when the nucleus, when the protons are really close together, you're trying to get them to stick to form what? Helium. Yeah. One proton, fire them together, you want them to stick to form helium. Right? But what's the charge? +1. What's the charge of +1? So what is happening? Repel. So if there's not enough energy, when you fire them together, they'll just bounce away. You need so much energy so that they'll stick, because they naturally want to repel. What they do here is, basically what they do is, you have your hydrogen. I mean, there's many different ways to do it, but one way which I've seen, which they're studying, is you have your hydrogen. What form is hydrogen? Gas. So if you want to hold your hydrogen, you give it a positive charge, and then you put a big magnet around it, so a big sphere of a magnet, and you keep the hydrogen focused in the center of the sphere of gas. Then around the magnet you have lots of lasers. You fire the lasers into the gas, and the gas heats up. What happens when things get hot? So what happens to the hydrogen? It'll start to move faster. But it cannot escape the gas because of the magnet. So what will happen is if you give it enough energy, when they collide together, they'll stick and they form helium. Then the helium will release energy. What form will the energy take? Heat. So what you're doing is you're making a small sun. You have a hydrogen gas, you fire lasers at it, and it'll start to heat up. So in fact you're making a mini sun. And it's completely safe. In fact, it's a very unstable process. The machine will only run for 2 or 3 seconds. Because as you can imagine, it's very difficult to keep the gas contained. Your magnets have to be perfectly balanced, and one imbalance and the gas will just release out and it won't stay balanced in the center. Okay? This is what happens in the sun. The sun is made of what? Gas. Which gas? It's hydrogen and helium, isn't it? Well, it doesn't matter which it is. It's a gas. There's a big gas, so there's gravity. Gravity's trying to pull it together. Like what's the gravity force doing? It's pulling the gas into the center. Okay? If the gravity is strong enough, as it gets pulled in, the atoms will collide. The hydrogen will collide to form helium, and then what energy is released? Heat, which we feel right now. Okay? So this is probably the way forward for energy for Earth. Okay? Oil will run out, gas will run out, the uranium is not safe, it will kill you in an explosion. I really think that this process, nuclear fusion, is the future. You might say, well, what about solar? Well, solar only works if you're in a hot country with sun all year round. What about wind? Well, the same. It'll only work in a place where there's lots of wind year round. True.
You have wind, right?
We do, but not as much as we should. But anyway, this will work in every country. And hydrogen is very easy to get. For example, what's in water? Hydrogen. And most of the planet is water. So there's plenty of energy there for thousands and tens of thousands, hundreds of thousands a year. The problem at the moment is cost. Cost. Expensive. Alright. I have some questions here. You can just take them with you. By the way, I encourage you to look at Google and type in online homemade nuclear fusion. There are some people who have made nuclear fusion in their basement. The only problem is for their machine, the Q2 and the Q1 are nearly the same. So it's just for fun. Yes, exactly, just for fun. Huh? Yes. I went to Google homemade fusion in my basement or something.
Never had a homemade fusion.
No, this
Instead of homemade fusion.
it'll get you into a lot of trouble.
That's how you homemade fusion.
I would encourage you not to do this. Thank you.